Okay, any questions about quizzes, tests, material to be covered? Then I'm going to share my screen. Basic chemistry for biology. Why do biologists need to understand chemistry? Well, it's because all life is composed of matter. Matter occupies space and has mass. And living things are made up of chemical reactions. Chemical reaction has reactants and products. A plus B go together and make C. So each of us is largely a set of chemical reactions, all going off simultaneously, making us into the living things that we are. So life is really chemistry. We're going to talk about atoms. Atoms are the smallest components that an element can be broken into and still retaining the properties of the original element. We are made of so-called star stuff, the same materials that make up stars. So when the universe began with the Big Bang, it was largely hydrogen. But these hydrogen atoms were fused into helium atoms, and helium then went on with time and conditions to make heavier elements such as carbon and oxygen. Now, these elements were released into the universe, and here on planet Earth, when it finally became a planet, these elements became the building blocks for new molecules for both living and non-living things. Now, what is an element? It's a material that's made up of just one type of atom. It's called an element. So each element is represented by a chemical symbol, usually a single letter, but it can be two letters. They're organized into a chart called a periodic table. It's organized, this table is organized on the basis of similar properties, similarity between various elements. So here's an example of a periodic table. There are 94 naturally occurring elements in a table, and about 25 of these are found in living things. The four most common, and these are the ones that you should remember for sure, are carbon, hydrogen, oxygen, and nitrogen, CHON. That's the mnemonic by which I remember them, John. And if you look on the periodic table, those three of those elements are elements 14, 15, and 16, right next to each other in the chart. And the other, hydrogen, is over here at element number 1. Now, each of the little boxes in the periodic table has a lot of information in it about that particular substance. That's shown here. So one of the numbers is one of the designations is the atomic name. So in this case, that's cobalt. The chemical symbol is CO. Atomic number is 27. Atomic weight is essentially 59. And on the far right is the electron configuration. We'll talk about each of these in turn, but in each little box, you'll see all of this information. Again, the major elements in organisms are these four, with these chemical symbols and these atomic numbers: 6 for carbon, 1 for hydrogen, 7 for nitrogen, and 8 for oxygen. And these 4 elements make up about 95% of any living thing. There are the so-called minor elements. I won't go through and name them all, but these are essential for life, but they make up less than 1% of the total mass of living things. And then there are so-called trace elements. Again, these are present in very, very small quantities, but they're still essential for normal growth and function. So they make up less than 0.01% of the mass of you or me. Why do we need all of these things? Well, for a lot of different reasons. They're listed here: calcium in bones and teeth. Magnesium is a cofactor, and we'll talk a lot about cofactors later when we talk about enzymes. Iron, as you know, is needed to carry oxygen in blood. Sulfur is a component that's very important in proteins, in the structure of proteins. Copper is found in hemoglobin, and potassium for nerve transmissions. How do we get elements into our bodies? We eat them. And this is a typical label from a daily vitamin supplement. So you can see that there are a lot of different components in vitamin supplements, and usually they're at the percent recommended value or they exceed it. Now, what is an atom? What are they composed of? I have to tell you that Scott is entirely responsible for what's coming next.
Oh, jeez.
Oh, no.
You can laugh now. You guys are laughing. Well, you'll enjoy it.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months.
2 minutes? You're crazy, you know that?
I can teach you about the atom in 2 minutes. Will you go back to school and finish out the year? How about it, huh? Come on, you're a betting man. How about it, Arnold?
Yeah. Yeah, okay, sure. You got it.
I got your word.
Yeah, you got my word. And 2 minutes.
We got a deal.
Yeah, we got a deal.
All right, sit down.
Okay.
There are 3 gangs on the street, right?
Yeah, 3 gangs.
And this right here is the territory. Now, here is a neighborhood. Got that?
Yeah.
And right in the middle of this neighborhood is a gang called the New Boys.
Yeah, the New Boys. Good name.
Okay. Out here on the outside of the neighborhood, on the edge of the neighborhood, is another gang. You know, these are real negative dudes, really negative, right?
Right.
Now, they call themselves the elected ones.
All right, the elected.
You got that? Really negative. They don't like nothing.
Right.
Now, they all the time out here circling around the neighborhood, just circling, you know, checking out the New Boys. Now, the New Boys see this. And they get, you know, they figure there's something wrong here, so they make a deal with another gang. A gang of very happy-go-lucky guys. They call themselves the Pros. The Pros. Now, the Pros are very positive cats. You see, they got all the good-looking women, right?
Yeah.
Right. See, now the Pros and the elected ones, an interesting thing, they hate each other. So much so that they keep the same number of members in the gang, just in case you did.
Right.
So if I got 10 elected ones, how many Pros do I have?
10.
All right. Now, how many gangs do I have?
3.
Name it.
The New Boys, the elected ones, and the Pros.
All right. Who's here?
The elected ones.
All right. Now, what are they? Negative?
Yeah, negative.
All right. Now, who's positive?
The pros, and you running out of time.
All right. Now, you see right here, the pros and the new boys, they call their hangout the nucleus. Yeah. Now, see, that's a real tough word. It's Latin. I kind of think it's Swahili, and it means center.
Yeah. What is it?
It's nucleus. Say it.
Nucleus. Is that really African?
Say it.
Nucleus.
You got it?
Yeah.
All right. Give you another Swahili word. It's a tron. It means dude.
Yeah. Tron. Dude.
All these gangs like that name so well that they all decide to use it. For instance, the pros right here in the middle start calling themselves protons. And the new boys, well, they start calling themselves neutrons. And out here on the edge here, the elected ones, they start calling themselves the elect.
The electrons, the protons, and the neutrons.
Yeah. And all this right here, this is the neighborhood. This is block after block of nothing. You understand block after block of nothing?
Yeah, I know all about that. And your time is up, Professor DJ.
Good. I was finished anyway. Now you going back to school.
School? Man, all I know about is a bunch of damn gangs that live in a round neighborhood.
Arnold, that's the atom. That's it, man. That's it. What's this right here?
Protons and neutrons.
All right, they call this the what?
Nucleus.
All right, what are these guys up here?
Electrons.
Are they negative or positive?
Negative.
And how do they move?
Round and round.
And if I got two of them, how many protons do I have?
Two.
Now, protons negative or positive?
Positive.
All right, and what's all this right here?
Oh, that's the neighborhood.
Which is?
Nothing.
You got it, man. You get an A.
Was that fun? You chemists?
That was factually accurate.
Wasn't a big game.
The atom is in fact a gang neighborhood.
Yes, it is. School, they got geometry and English, biology. I just don't understand the thing about it, man. I just don't get any of it.
What about chemistry?
That's the hardest one.
Let's see.
Did they teach you anything about the atom?
Atom, year after year, and I don't know the first thing about it.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months.
Sorry about
2
that.
minutes. You crazy, you know that?
Okay. All right, you just heard about the gang view of composition of atoms. So atoms are composed of protons, neutrons, and electrons. Protons with a positive charge, neutrons no charge, and electrons with a negative charge. You can make an analogy between an atom, the smallest component of matter, and a solar system. In both cases, you have a center, either a nucleus or a star, around which items are rotating. And so the speed at which they're rotating makes a centrifugal force. And so that force is moving them out away from the nucleus. However, in the case of an atom, the electromagnetic attraction between electrons and protons draws them in. And so the balance between those two forces keeps them in particular orbits called shells. And similarly, in a solar system, these planets are spinning. That causes a centrifugal force throwing them out, but magnetism is drawing them toward the star. And the balance between the magnetism and the centrifugal force keeps planets in their orbits. So let's talk about protons. They're found in the nucleus with a positive charge. The number of protons determines the type of atom it is. The number of protons equals the atomic number. So the atomic number of cobalt is 27. It means there are 27 protons in a cobalt atom. The atomic number of carbon, for example, is 6. Oxygen is 8. And hydrogen is 1. So in an electrically balanced atom, the number of protons is equal to the number of electrons. Protons are positive, electrons are negative. If they're equal numbers of each, the charge on the atom is neutral. And the number of protons is approximately equal to the number of neutrons, although not always exactly. Neutrons are also found in the nucleus. Protons plus neutrons is atomic mass or atomic number. That's this number right here, 58.9 for cobalt, and that rounds to an atomic weight of 59. Now, electrons are so small, they don't contribute to the mass in a significant way, so they don't count. They count for their electrical charge, but not for their mass. So for cobalt, the atomic weight of 59 minus the number of protons, which you see from the table is 27, that equals the number of neutrons. So from the periodic table, you can figure out how many of each component of an atom there is. Electrons, number of electrons is equal to the number of protons in the atom. The electrons orbit around the nucleus, and they're distributed in shells, and the shell is determined by the two forces I mentioned earlier, the centrifugal force throwing them out and the electromagnetic attraction pulling them in. So they stay in their orbits, in their shells. So then what is an isotope? An isotope has the same number of protons and electrons, but a different number of neutrons. So remember that the difference between an ordinary element and an isotope is the number of neutrons. The examples, carbon has various isotopes, phosphorus does, and sulfur does, and these are used experimentally as tracers. Well, what about the orbitals? Each one has a maximum number of electrons that it can hold at any one time. So the first shell, or orbital, of any atom can hold a maximum of 2 electrons. So that's a constant. The first shell of any atom has 2 electrons. The second shell can hold a maximum of 8. And they're more energetic than the ones in the first shell. But the most stable condition for an atom is when its outermost shell is filled with electrons. So the first shell has 2, the second shell can have up to 8, and if it does, stable. So that means that there are reactive and unreactive atoms. And examples of that are shown here. The outermost electrons are called valence electrons. They're the ones that are in contact with the exterior, with the world. And their number and position determines the chemical behavior of the atom. So atoms with the outermost electron shell filled are stable. They won't react with anything. And if their outer shell is unfilled, they can be reactive, in some cases very reactive. So you have three examples here. Hydrogen, the hydrogen atom, its outermost electron is unfilled. It would like to have two, but it's only got one. Helium, on the other hand, has two electrons in its outermost shell, so it's full. Carbon has four in its outermost shell. It would like eight, so carbon is very reactive. Helium, or I should say neon, on the other hand, has eight, so it's an inert gas. Sodium has 8 electrons in its second shell, but it has a third shell. And that third shell has only 1 electron, which makes it very unstable. Argon, on the other hand, has 2, 8, and 8. So again, it is an inert gas. So atoms in living systems. Here we're back again with carbon, hydrogen, nitrogen, and oxygen. These are the 4 main elements in living things. Hydrogen is reactive because it's only got 1 electron and it would like another. Carbon is very versatile, very reactive with a lot of things because it has 4 electrons in its outermost shell and it wants 4. Nitrogen has 7, so it has 5 in its outermost shell. It's looking for 3, whereas oxygen is looking for 2 to make itself stable. So atoms with unfilled outer shells can become more stable by acquiring electrons or by sharing electrons with other atoms. And when this happens, a chemical bond is formed. Now this is very important. You need to understand this completely because we're going to talk about types of bonds, and the different types of chemical bonds are critical for the molecules that make up living things. So the 3 that we're going to talk about first are ionic, covalent, and hydrogen. And I've put in red here the things that you should remember about each type of bond. An ionic bond forms when opposite charges attract each other. A covalent bond forms when 2 atoms share electrons. So remember, the word share goes with covalent. Hydrogen bonds are formed when there is an electrostatic attraction between a hydrogen atom and a polar molecule. I'll talk about that in a little bit. So what you see here is an example of a covalent bond, where you have 2 hydrogen atoms. They're both unhappy because they have 1 electron and they'd like 2. So if they share if they share the electrons that they have, they can now each have 2, and that makes a hydrogen molecule. So what is an ionic bond? Well, in the case of an ionic bond, you have an atom that transfers an electron to another atom. And when it does, it now becomes positive. So it gets rid of a negative charge, which makes it a positive ion. And similarly, the atom that receives that electron now becomes a negative ion because it's just received a negative charge. So now there are 2 ions, one with a positive charge and one with a negative charge, and they attract each other, and that forms a bond which is called an ionic bond. It's a relatively strong bond. So the definition of an ionic bond is most common when an atom's outermost orbital contains just one or two electrons or needs one or two electrons. Salt is one of the best examples of ionic bond. If you have a sodium atom, salt is sodium chloride. Sodium atom, which has a second orbital, which is full with 8. Then it has an additional, a third orbital that has only one electron in it, which makes a sodium atom very reactive. A chlorine atom, on the other hand, has 7 electrons in its outermost shell. So it would like 1. So if sodium contributes its 1 electron that it really doesn't want to chlorine, now sodium becomes a positive ion. As it's lost a negative charge, it means it becomes positive. Chlorine, if it accepts that electron, now becomes negative. It's accepted a negative charge. And so these two ions, the plus ion and the minus ion, attract each other, and that is the ionic bond. Does that make sense to everyone? That's an ionic bond. So remember how they form. And that it's a relatively strong bond. This shows the same thing. The point here is that the positive ion is called a cation, and the negative one is called an anion. So in a crystal of salt, what you have are all these ionic bonds between sodium atoms and chlorine atoms, which hold the compound together. It's an ionic compound, NaCl. Now let's look at covalent bonds. And remember, the key word with covalent bonds is share. Covalent bonds involve 2 atoms that share electrons. So 1 or more pairs of outer shell electrons are shared. And you see that happen here. We've seen this before. 2 hydrogen atoms share their electrons to make a hydrogen molecule. So you can represent a covalent bond in a number of different ways. So in the case of hydrogen, it can be H2, or it can be H bar H. And that bar represents a single covalent bond. There can be double covalent bonds. So for example, in the case of carbon, each has 6, I think this is oxygen. Each has 6 electrons in its outermost shell. It shares 2 pairs of electrons. So now they both have 8. And yeah, this is oxygen, and it's can be represented as O2 or O bar bar O. So a covalent double bond is represented by 2 bars. And I want to make the point here that there can be a double covalent bond or a triple covalent bond. So we've just looked at oxygen, where 2 electrons from each atom are shared. So you get this configuration, and that's represented as O double bond O. In the case of nitrogen, if you form a nitrogen molecule from 2 nitrogen atoms, now there are 3 electrons from each that are shared. So that is represented as N bar 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 N, or N2. Examples of covalent bonds. Carbon is the most common denominator for biomolecules. Anyone know why? Give me your name first if you have an idea why.
Brian Yee, is it because it can bond with a bunch of atoms? It can have 4 different bonds.
Yeah, that's true. It has the capacity to bond with a lot of other kinds of atoms, but why?
This is Marcus Kerbrock. Is it because it has a lot of electrons that it can share?
Well, what do you mean by a lot?
Like in the valence electrons.
Yeah, the valence.
Doesn't have, it has like 8, so it's like filled, so it can give some away.
Yeah, it has 4. So
Sorry.
you can either look for 4 more from another atom, or it can give up 4. And so, but it's very good at sharing. So if it shares 2 of its 6 outermost, excuse me. If it shares its outermost electrons, and it can share them with a lot of different things, but what it's always trying to do is pick up to share sufficiently so that it has 8 electrons in its outermost shell. And that's stated in the second point here, that carbon readily reacts because it needs 4 electrons, and it finds 4 more by sharing. And remember, a covalent bond is defined by sharing. And in fact, there's a whole discipline, organic chemistry, that studies nothing but carbon compounds. So let's think a little bit about chemical formulas. In writing formulas, a number that is subscripted means that there are 2 or more atoms of that element. So here are examples. O2 means there are 2 oxygen atoms. CH4 means what?
4
Uh,
hydrogen.
oh. Go ahead.
4 hydrogens with 1 carbon. They're connected.
Say it again.
4 hydrogen with 1 carbon. They have.
Yes, 1 carbon and 4 hydrogens. And what about H2O?
S1, Monzon speaking. It's 2 hydrogens and 1 oxygen.
Right. Did anybody recognize the last one? C6H12O6?
Esteban Monzon speaking again. Isn't that just glucose, like photosynthesis?
Yeah, it's glucose. 6 carbons, 12 hydrogens, and 6 oxygens. So in writing chemical formulas, the number in front of a formula indicates the number of molecules. So if there's no number in front, it means there's just 1 so molecule. But if there's a number in front, this would be 3 methane molecules, 12 water molecules, or 7 glucose molecules. And now to complicate things a bit further, there are both polar and non-polar covalent bonds. And this is important because it leads to our third type of bond. So when electrons are shared equally between atoms, the molecule is non-polar. And such molecules are hydrophobic. But when the electron positions are skewed to one side of the molecule, it's polar. So if you look at the top center here, that's methane, it's non-polar because the electrons are equally distributed around the molecule. But if you look at water on the left here, you can see that on the side with the two hydrogen atoms, it has a plus charge, and with the oxygen atom, it has, well, that's wrong, that should be a minus charge. Oxygen should be a minus charge. And so a non-polar covalent bond, the electrons are distributed equally. In a polar, they're skewed to one side. So some atoms are more electronegative than others. So oxygen is one that's more electronegative. So here again is a water molecule. The oxygen atom is the large one, and the electrons tend to congregate on the oxygen side of a water molecule, giving it a negative charge, which means that the other side, the hydrogen side of a water molecule, has a positive charge. Now, these charges are very small, very slight, but they're significant. So in biological systems, the molecule, the ones that tend to be electronegative are oxygen, nitrogen, and chlorine. This pretty much shows the same thing that I was just trying to say. You have the oxygen atom is more electronegative on one side, which leaves the hydrogen atoms more positive on the other side of a water molecule. So water is a polar compound. This is just another representation of the same thing. This big orange oxygen atom is electronegative, leaving the two hydrogen atoms electropositive. That leads us to a hydrogen bond. And hydrogen bonds are very important. Life couldn't exist without hydrogen bonds. So what is it? It's an electrostatic attraction between a hydrogen atom in one polar molecule. For example, water is a polar molecule, and an electronegative atom in another polar molecule. And that electronegative atom can vary. It can be oxygen, it can be nitrogen, it can be something else. So because hydrogen, oxygen, and nitrogen are common and abundant in biological systems, hydrogen bonds are very common, but they're weak. Weaker than covalent, weaker than ionic. They're easily formed and easily broken. And that is a very important feature of hydrogen bonds because, for example, the DNA double helix, which we'll talk about next, would be impossible without hydrogen bonds. Protein folding, and proteins have to be folded properly in order to have activity, require hydrogen bonding. And for example, the specific heat of water is high because of hydrogen bonding. If it weren't for hydrogen bonding, water would boil at 80 degrees centigrade instead of 100, and oceans and lakes would boil away. They'd evaporate. We wouldn't have liquid water here on Earth. So this illustrates once again a hydrogen bond. So again, it's important how electrons are skewed in polar molecules. So this is hydrogen bonding, between two water molecules, H2O. So hydrogen bonding always involves a hydrogen atom. And in this case, the hydrogen atom on this water molecule has a slight positive charge. And we know that oxygen in a water molecule has a slight negative charge. These two opposite charges attract each other, and that forms a bond. The hydrogen bonds are almost always represented by dotted lines. So this is a hydrogen bond, a dotted line between a hydrogen and an electronegative molecule, which in this case is oxygen. So it does not need to be oxygen. It can be another electronegative atom. Now, this shows hydrogen bonding among several different water molecules. So what you should notice here is that the orange is oxygen, it's negative. The white is hydrogen, it's positive. And so every one of these hydrogen bonds is between a hydrogen and an oxygen. It's just that their orientation changes so that they can be in proximity to each other. And this shows the lattice that can form among water molecules if all the hydrogen bonds are made that is possible to make. Water is a very unusual material. It's unique. And it has a number of properties that are dependent on the fact that it hydrogen bonds. It's abundant on Earth and elsewhere in the universe, and its special properties are due to hydrogen bonding. It covers about 75% of the Earth's surface. We ourselves are mostly water, up to 95% water. It's the only substance on Earth that is found in all three states of matter, solid, liquid, and gas. It has a neutral pH, either acid or base, and I'll come back to that at the end of this presentation. It's a universal solvent. It dissolves more substances than any other liquid. And it has what's called a high specific heat, which means it can absorb a lot of heat without itself changing temperature. So it's a coolant. And because there's so much water on the planet Earth, it tends to cool the Earth. It doesn't become overheated by the energy from the sun. Now, this is important. It will come up again, the three forms of water and why they are the way they are. So if water is solid, if it's ice, it means all the water molecules are hydrogen bonded to other water molecules.
Are compacted.
In ice, every water molecule is bonded to at least one other water molecule. In liquid water, there's some of each. Some water molecules are hydrogen bonded and others are floating free. Whereas if water is a gas, none of them is hydrogen bonded. So to remember that, in ice, it's all. In gas, it's none. And in liquid water, it's some of each.
And also, teacher, the movement of molecules is different from the three solid. For example, solid has very low speed of movement. The molecules in the liquid is higher, and the gas is higher.
Yes, you're right. In the case of ice, where they're all hydrogen bonded, they don't move at all. They're stationary. They make a lattice. In the case of water, some are moving and some aren't. In the case of gas, they're all dancing around. Okay, everybody clear on the different forms of water and how hydrogen bonding determines them? Okay, as I said, water has a high specific heat. The solid phase is less dense than the liquid phase. That's very peculiar. A high heat of vaporization. It's a good solvent, and it has both adhesion and cohesion properties. So let's think about those. Specific heat means the amount of heat energy required to raise the temperature 1 gram by 1 degree centigrade. So raising the temperature of liquid water takes a lot of heat because much of the heat is used to break the hydrogen bonds that hold water together. So as I said earlier, the huge amounts of surface water on the Earth act like a thermostat to moderate daily temperature. Every day the sun shines on the Earth, releasing a lot of energy, a lot of heat on the Earth's surface. But to avoid the Earth becoming extremely hot during the day and extremely cold at night, as other planets and other solar systems actually do, water moderates it so that the temperature changes very little between day and night on planet Earth. The water is less dense as a solid than it is as a liquid, which means that ice floats. In the case of ice, where all the water molecules are hydrogen bonded, if you put that in with liquid water, where some are bonded and some aren't, the ice is less dense and it floats. And that is very important. What would happen if it didn't float? Well, here you see a picture of a mountain lake showing this would be in the winter. Air temperature is much lower than freezing. The ice temperature is freezing. It's at 0 degrees. The water temperature below the ice is higher than freezing. So at the surface, it's 0, and as you go deeper into the lake, the water gets warmer and warmer. The floating ice is like insulation. It insulates between the air temperature and the water temperature. And the deeper in the lake, the warmer the water gets. So this allows aquatic life to persist even during the winter. So if you think about it, if ice didn't float, if it sank, the oceans in the winter would fill up with ice, leaving no opportunity for aquatic life in temperate zones. Heat of vaporization, why do we sweat? Because
Excuse me, Professor. The solid, the snow, it's flow because it's become less density.
the solid is less dense.
Yeah, it's when the hydrogen bond it's become together. That's what make it less density.
Yes,
And yeah, and that's make it flow on the water.
that's right. Yeah, because of the 100% hydrogen bonding, it is less dense.
Yes.
That's unusual for substances because usually for most substances in their solid state, they sink.
Yeah. Thank you.
Yeah, so when you sweat, you lose a lot of heat because a lot of heat is required to change water from its liquid state to its gaseous state, evaporation. Okay, this essentially is saying the same thing. And this is important for plants because evaporation of water from the leaf surface helps keep leaves cool. And remember, leaves are out there in direct sunlight, and so they're being subjected to a lot of heat. And if they were not able to keep cool and by means of evaporation, they'd shrivel up and wilt. Solvent properties. So what happens when a substance dissolves? And again, the dissolving of a substance depends on hydrogen bonding. So we'll take the case of sodium chloride. Water is polar and forms hydrogen bonds. The result, water dissolves many ionic and polar compounds. It readily forms solutions or with compounds or with charged ions, and it can be either hydrophilic and hydrophobic. So look at the diagram here on the right, where salt is being poured into a beaker of water. So what happens? Well, salt is a crystal. So undissolved sodium chloride is crystalline. It's composed of green chloride ions and blue sodium ions. Chloride ions have a negative charge, sodium ions have a positive charge. Remember, they form an ionic bond. It's the difference in charges that holds the crystal together. Now, when water comes along, water is a polar compound. Oxygen and water is the little red balls. And oxygen has a negative side. The two hydrogen atoms have a positive side. So when they come in contact with a blue sodium ion, notice that the oxygen atoms turn in toward the sodium. That's electrostatic attraction, plus and minus. Whereas with a green ball, a chloride ion, the opposite happens. Instead of the hydrogens turning in, now, instead of the oxygen turning in toward the chloride, the hydrogens do. And so as you go down the chart, the crystal keeps becoming smaller and smaller as the chloride ions and sodium ions are bonded to water molecules, until by the time you get to the bottom, every atom, whether it's a chloride or a sodium, is completely hydrogen bonded with water molecules. And when it's in that form, it's in solution. So it goes from a solid state to a liquid or a solvent state, simply due to hydrogen bonding. And now one last thing, adhesion and cohesion. I've circled these because I want you to remember them, remember what they are. So the number of hydrogen bonds formed by each water molecule give water molecules cohesive strength. So cohesion is a tendency of water molecules to stick to each other. And again, they stick due to hydrogen bonding. Adhesion is a tendency of water molecules to stick to other things, other surfaces. And that's really important for plants. Why do plants, how are they able to grow up and become very tall trees in some cases? Part of the reason is the adhesive and cohesive properties of water. So if you look at a plant, where does the water come from? It comes from the soil. So the roots take up water, it gets into the conducting vessels, the xylem, goes up the stem and ends up in the leaves. Well, the leaves have to keep cool, so they have little openings where water, liquid water can escape and become a gas. This is where a cohesion is important, because as the water molecules escape, because of cohesion, they pull the water molecules behind them up. So as the gas escapes, the liquid water is pulled up. Adhesion comes into play because of the xylem vessels are tubes, and the water molecules are attracted to the sides of the xylem vessels, and so it's constantly moving up because of adhesion. The tendency of the water molecules to stick to another surface. Is that clear? These two properties, cohesion and adhesion, are what allows water to move up in a plant. Surface tension is caused by hydrogen bonding. It's a measure of how difficult it is to stretch or break the surface of a liquid. And another point to make here is that molecules have different shapes because they exist in a three-dimensional formation, depending on the arrangements and numbers of bonds between their atoms. The bonds are usually flexible, and atoms can rotate around a bond so that they can change shape. And I've shown you a picture here at the bottom of two molecules in two different shapes. It's the same molecule, but the one on the right has twisted around its carbon-carbon bond so that its shape is different from the one on the left. We're carbon-based. I've talked about this before, but it's important that to note that carbon chains are the basis of most organic molecules. Most of the molecules we have in our bodies start as a carbon chain. Some molecules are only carbon and hydrogen. They're very important in life. They're called hydrocarbons. And I mentioned earlier that there's a whole field of study called organic chemistry, which looks at nothing but compounds that have carbon in them. Carbon that is covalently bonded to other atoms. Now, change the subject from atoms and bonds. I just want to, because there's no other place in the course to talk about this, I'd just like to mention pH, because you encounter pH so often in daily life, and yet it's not readily understood. So I want to make a point about pH and about buffers. So what you see here in this colored picture is a range of pH from 0 to 14. And then you see various different substances that we contact fairly regularly, which represent these different pHs. So for example, a pH of 0 would be like hydrochloric acid, a pH of 14, sodium hydroxide, a pH of 7, that's neutral, pure water has a pH of 7. There's some very acidic biological entities like in our stomach. Stomach acid is between pH 1 and 2. Lemons and apples and tomatoes are fairly acid. Banana, less so. Milk is slightly acid, whereas blood is slightly basic, but it's close to neutral. And this is important. So no matter what we eat or what we're exposed to, blood is always the same pH, always has the same hydrogen ion concentration. And interestingly, look at this, broccoli is quite basic. has a pH of 10. So what does pH mean? Look on the left. pH means hydrogen ion concentration. It ranges between 1 and 10 to the minus 14th gram equivalents of hydrogen per liter. So that's the definition of pH. And the number, the pH number from 0 to 14, that is an exponent of 10. Numbers range from 0 to 14. So if you take a substance that's pH 0, 10 to the 0 is 1. So that means that there is 1 gram of hydrogen ions per liter. So that is very high hydrogen ion concentration, and that is acid. At the other end of the scale, pH 14 really means 10 to the minus 14th. So 10 to the minus 14th grams of hydrogen per liter. So that's very low hydrogen concentration, and that's very basic. So if you're not already familiar with pH, on your own time, think about this and think of how much sense it makes to quantify hydrogen ion concentration in this way. So then what is a buffer? In biology, is an organic substance that neutralizes hydrogen ions. It protects a solution from a major pH change. Okay, I've run a little overtime. We really had 60 minutes today because you're taking 15 of your minutes to do the quiz. I think that's the last slide I have, yes. So is there quickly any questions or comments before we end?
Could you make sure that the slides are published? Because I looked on Canvas and I can't access them.
I put them in last night. Your Canvas container should have under modules.
I don't see it either, actually.
You don't? All right, well.
If you check files, it is
Files.
there, but it says that it's not accessible, like as if it's not published yet.
Oh, all right. Well, I will take a look at that right now and fix it.
Professor.
Yeah.
Also, what is on quiz 3 again?
Quiz 3 covers structure of life, life in the universe, and classification of organisms. Those 3 topics. Does not cover today's topic, chemistry.
Sorry, teacher, can you repeat that one?
The structure of life, the 3 topics covered by quiz 3 are the structure of life, life in the universe, and classification of organisms.
Thank
you. Oh, there's a test right now? I mean, a quiz?
The test is available all day today. So when you log into Canvas and you click on quizzes and click on quiz 3, and as soon as you do that, the time starts. You'll have 15 minutes from that point to finish the quiz. Okay, anything else? Remember,
and if you haven't taken the quiz yet, and now that you know some of the stuff that's on it, you can always stop in at workshop. We can cover those topics if you have questions before you go take your quiz.
Workshop starts on
Yeah, and the workshop starts at 2.
Okay.
All right.
Is there office hours today?
Office hours are 4 to 4:40 today. And you have the website. I sent you sometime earlier as an announcement, the website for my workshop or for my office hours. Office hours are every Monday and every Wednesday from 4 to 4:40. It's 40 minutes because that's all the time I'm allowed to hold office hours.
Sorry to interrupt, but for roll call, does it? I came in a little bit late. Do you still go over it, or
Over what?
the roll call? I came in a little bit late. I don't know if you.
Well, I don't. What I do is when you speak up, I try to make note.
Okay.
That's how I take attendance. People who speak.
I just make sure. Thank you, though.
Okay, anything else?
Professor, I have a quick question. It's like somewhat on the topic of this because you're talking about like acidic and alkaline, but and I know you're probably no nutritionist, but is there any like benefit to eating like only alkaline foods? Because you know there's like crazes out there, and one that got really big for a while was like being alkaline vegan, and I don't understand why just eating things that are alkaline and not acidic would be healthy.
It's a fad. It means nothing because when you eat something, what's the first thing that happens? It goes into your stomach.
Right.
Your stomach has a pH of about 2. So it's immediately exposed to a very acid environment. And that's when your food then is broken up. And as it moves down the digestive tract, the pH keeps going higher and higher.
Right.
Well, when we talk about the pancreas and cystic fibrosis, we'll talk about the digestive process.
Nice. Cool. Thanks.
Okay, anything else?
Have a good day, Professor.
Okay, take care, everybody.
Have a good weekend.
Have a good day.
All right, see you on Monday.